Hello and welcome back to Year 13 Integration Revision. I think this lecture number 7 if my memory serves me well, and tonight I hope to do questions 70 to 81, so a real mix again. Things will get a little bit harder now. Okay, I hope the microphone is not picking up any funny noises. It's been a problem the last few lectures, so I do apologize, not me if you're hearing anything funny taking place. Okay, let's go into integral number 70, which is trigonometric, is as standard as it gets. So integral 70 is 4 cos squared of x dx. How do we do that? This is a standard integral. You just need to know how it's done. It's done by trigonometric identities, and in particular your cos double angle rearrangement, which I've mentioned several times. The cos squared of x you can write, of course, as a half plus a half cos 2x. And the corresponding for a sine squared, by the way, it's exactly the same but with a minus in there. So we're going to swap this in the integrand for a half plus a half cos of 2x, multiply the brackets and integrate it. So what we're going to get for that is very, very simple. 2 plus 2 cos of 2x dx. 2 will integrate, of course, to 2x with respect to x. And we need to differentiate the sine of 2x to produce that. Sine goes to plus, that's good. And you also produce a times 2 to divide by 2 is 1 plus c. So that's number 70, all done. Number 71, 72, oh my god, loads of trig. I think we have to go to 76 where the first non-trig integral comes up. Okay, 71 from memory, because I often use this particular book for revision with my own students. The weakest students for 71, 72, they have real issues. They're kind of tough. 71 is 1 plus tan squared in a bracket. 1 plus tan squared, we should kind of recognize it, and multiplied by a sec squared. Okay. I think when I wrote this question, I really playing with you. I really want you to write this as a sec squared. Is it sec squared? Yes, it is. So what you get in there is, in fact, sec squared times sec squared, sec to the power of 4. This is a problem. It doesn't work. In fact, if I gave you to integrate a sec to the 4 of x, what you will need to do, dx of course, what you would have needed to have done is actually to write it like this. So you actually, by doing this, you're moving further away from the way this is meant to be done. Okay, so let's have a little think about this one. We got a bracket. Might have tried it like this and then I would have thought, now what? Okay, but if we multiply the bracket and we think about it sensibly, the sec squared will integrate instantly, don't forget, because sec squared comes from a differentiation of a tan. What about the sec squared tan squared x? Do we recognize it? Well, if you don't recognize it, then what we would have done is probably switch into sines and cosines or try something else. So let's proceed by multiplying the bracket and let's see what happens. So, sec squared of x plus tan squared of x sec squared of x dx. So the real problem is this one. This is just a tan when it's integrated. So what about this one? Now this now is where things get a little bit harder. This particular bit, if you want, if you can't recognize it, because of course I hope many of you can actually recognize it and write an answer. The only thing that will actually open it up is the substitution u is equal to tan x, just for this bit here. Incidentally, I just want to say for this particular integral, I'm not going to do it, but if you're taking notes, the entire thing, if you just don't multiply it and you use the substitution u is equal to the tan of x, it will probably work. It's got to be a work to be done, but it will actually work. So this is worth a try. But for those who now, okay, you can actually split into 2 bits here. So what I'm suggesting you do here, if you multiply the bracket, is to write as a sec squared of x dx plus another integral, tan squared x sec squared of x dx. This, of course, you'll be able to integrate it, I hope, you can see it comes from a differentiation of just simply tan x. And this particular one, you can use this particular substitution, but as I mentioned, I'm not going to do it by substitution. I'm expecting to start recognizing some of these things. Sec squared next to a tan, any tan, tan to the 1, tan squared, tan cubed, tan to the 4 is very special because this is the differential of the tan. And therefore, this particular expression comes from differentiating a higher power of tan. It comes from differentiating a tan cubed. What will happen when you differentiate that? Well, a third will come to the front. Not a third, sorry, I'm very tired and I'm saying stupid things. A 3 will come to the front. I was giving you actually the answer to this. Okay, a 3 will come to the front. The tan will reduce its power down by 1 to tan squared of x, and then times the differential of a tan, which is a sec squared of x. So we have this bit here except the 3, so we need to take care of the 3 by dividing by a third. So this is kind of tough, this particular integral. So I'm going to write the answer up there, no substitutions. This comes from differentiating a tan x, and this quantity comes from differentiating a tan cubed, but we need to put a third in front of it in order to make it work, plus c. Okay, I hope you can see all these kind of things. It's not the most straightforward one. So the next one is pretty much on the same theme. So I will leave this particular one up before I copy number 72. I just glanced at it. Number 72 is very similar looking. Tans and secs again with squares. So this one is probably slightly easier. 1 plus the tan of x in a bracket, and next to it a sec squared x dx. We can follow a similar logic because practically we got the same thing apart from that being squared there. So one way of looking at it is to multiply the bracket out, because I know I can integrate at least a sec squared. So sec squared x plus just tan now with a sec squared next to it dx. And what happens here? Well, this, I'm going to start my integration. Again, the substitution for this part, u is equal to tan x, works, but we'll try to recognize it. Now we're on number 72, and we should try to actually see if we can actually spot what is going on in there. That comes from a tan of x. That's the sec squared. Tan differentiates to sec squared. Now a tan, any power of tan with a sec squared next to it, is just a higher power of tan. So that, because it's to the 1, starts life as a tan squared of x. And what we need to do is we need to differentiate it to see what constants we need to adjust. A 2 would have come to the front. Why am I writing a half? I don't know. I'm just very tired tonight and I'm giving you the answers actually. Okay, a 2 would have come to the front when I differentiate that. The tan will go to the power of 1, like I'm seeing it there, and the whole thing would have been multiplied by sec squared. We got everything apart from this 2. We need to take care of that 2, we need to hide it, add an integration, therefore we need to divide by 2, so that should be a half tan squared x plus c. Is there another way we can do that? Some people that can actually recognize this can actually say, it doesn't really matter, I don't even need to multiply it all out. I see there a bracket, let me just write it here, 1 plus the tan of x to the power of 1 at the moment. What happens if I differentiate the interior of this bracket? Well, quite clearly that gives me nothing, but the tan of x will produce a sec squared of x. What does that mean? Well, that's the derivative of the interior of the bracket, which means this bracket could have started at the power higher if you want. So in fact, I don't need to write anything, I can just integrate it on the spot. That's an alternative approach. Start with the bracket, 1 plus the tan of x all squared. What happens when you differentiate it? 2 will come to the front. The bracket will go 1 plus the tan of x to the power of 1, and by the chain rule, I'm gonna get a sec squared of x. So if I see what I've got in the integrand, I've got everything apart from this 2. Therefore, stick a half in front of it, and you're done. And I just want to point out to somebody to some people rather, that can see other things in there. Yes, there are other things. If you look at this particular line, they're not worth discussing perhaps because they're a little bit silly. If you look at, I think when I multiply the brackets and I have there a sec squared of x plus tan x sec squared x, that's okay, that comes from a tan. But this can give you an alternative form. It's very, very special. Not a lot of people can see this, and you shouldn't really, because it's not normal, it's not natural, it's silly perhaps. I can write the tan sec squared x as a tan sec x, borrow one of the secs from there, and then a sec of x next to it. So that's exactly the same. Now, sec tan is the derivative of a sec, which is telling me this was a higher power of sec. So this, I can actually integrate it. So let's put dx there. So that's just for this section here. Okay, it would have started as a sec squared of x. When I differentiate it, it produces a 2 to come to the front. The sec goes to the 1, and then it produces its differential, which is sec tan. All I need to do is take care of this half. Not this half, this 2. So I need to put a half in front of it. Loads of slips of tongues tonight, so I don't know if I'm gonna complete this lecture without any mistakes. Okay, it's not even late tonight. Tonight I'm actually filming, what's the time now? It's just after 9 o'clock. Maybe it's been a long week. Okay, number 72, number 73, and number 74. Trigonometric, evil looking, but actually deceivingly easy. Okay, sometimes if you go absent-minded on these 2 that are coming up, you can write silly things for very simple integrals. Okay, this is the number 73. First of all, we've got the cosec squared of 3x plus 1. All you need to do for something like this is to know your differentials. First of all, let's not think of stupid things such as this is a cosec squared multiplied by 3x plus 1. Cosec squared, it has no meaning. This bracket is the argument of the trig function. So that's one lump basically. Is cosec squared easy to integrate? Well, the answer it is, because there is a standard differential which says if we differentiate a cot of x, will produce a minus cosec squared of exactly the same argument. So when we look at this, well, quite clearly that must have come from the differentiation of a cot of exactly the same argument. This will produce, of course, a minus, so we need to take care of the minus because cot differentiates to minus cosec squared, and here we have a plus, but we also have to take care of a little chain that times 3, so it needs a third in front of it, plus c. Nothing else to write. It's as simple as that, this particular one. Okay, number 74. Very similar. The cousins. 12 sec squared of an argument 2x plus 3. They're done exactly the same way. We're just wondering, that's something differentiates to sec squared. I'm not even going to write it down. Of course, you should know tan differentiates to sec squared of exactly the same argument. And therefore, this started life as a tan of 2x plus 3 before it got differentiated. Tan differentiates to plus, so we don't need to worry about plus and minuses. It also will produce a times 2 to come to the front. So we need to divide by 2. This time we have a 12 in front of it, and therefore 12 divided by 2 is 6, plus c, and that is, I didn't put the numbers actually, sorry about that, is number 73, this one, and 74. And we hope to go up to number 81. All right. Number 75, a little bit of trig on the next integral as well. Number 75, it doesn't look very pretty. is the sine of the square root of x over the square root of x dx. Okay, looks a little bit scary with the square roots in there. Okay, I'm going to do it two ways. I'm going to do it first of all the way most of us should be thinking about it. I mean, when you're looking at this particular integral, you should be thinking, okay, I've got a problem in there. I really do not like the look of this square root of x, and if I don't like its look, it's worth trying a substitution. Get rid of it, basically. Okay, so I'm going to try the substitution on the side here. U is the square root of x. With square root substitutions, you're advised to first of all square your substitution before you differentiate it. So u squared is equal to x. You can differentiate implicitly here, for those who have seen implicit differentiation. 2u du by dx is equal to 1. But for this particular one, you can actually write it back to front. I'm going to do so you can see what I'm doing. Oops. X is equal to u squared. Let's take that a little bit off. And now, instead of doing du by dx, we can do dx by du. So dx by du will be equal to 2u. And of course, we want the dx bit to be replaced. So our dx will be, of course, 2u du. And we are returning now to the integral. And see how that changes things. Okay, we call the square root of x u. So that's good news. So therefore, the sine of the square root of x will be the sine of u. And our dx is 2u du. 2u du. So that's a multiplication if you want. And this is brilliant because, first of all, the u's will cancel. And this will simplify to 2 from there. Sine u du. That's a very simple integration to do. Sine comes from a differentiation of a cos. Cos differentiates to a minus. Take care of the minus. And there's no change there, and therefore the 2 must have been there from the beginning. And all we need to do is just basically go back and replace our u, which of course is the square root of x, in the final answer, so we get full marks in an exam. So 2 cos of the square root of u plus c. And I did mention there is another way of doing this. People can actually recognize this. Some people that are sort of like on the top end in their exam standards, if you perhaps write it first of all as sine of x to the half, that's the argument of your sine, and you look at the x to the half at the bottom, and maybe go another line and just say, you know what, this x to the half I can write to the top as x to the minus a half, sine of x to the half. Okay, and just pause for a second and say, oh, well, you know, the interior of this bracket, the argument of the sine, when I come to differentiate the x to the half, this produces a half the power of the x to the power of minus a half. Okay, and I see this x to the minus a half at the front. So it's telling me it's not a higher power now, okay, but we need to differentiate something that has this as the argument, but it goes into sine of x to the half. And quite clearly, that is the cos of x to the half. The cos of x to the half will go into a minus, so we need to take care of that minus, but you also produce that times a half when it came to the differentiation of this, and therefore 1 divided by half, it should give us the same answer. If you can't quite see that, do not worry. Please stick with substitutions where possible, because that's the most important thing. This comes with time, and sometimes even with a lot of practice, there'll be days where you'll be tired and you won't see it, and other days you'll be seeing it. So it's not the way forward as your main technique. Use safer techniques that can always, not can always, but they're more likely to produce sensible answers and with less risk, if you want. Okay, that was number 75. Number 76, a joke. It's just there to add a little bit of bulk. So if you've been absolutely beaten by these integrals tonight, at least we can take a breather with this one and laugh at it. 6e to the 2x plus 2. So this one should be straightforward. Quite clearly, it's just an exponential with, of course, exactly the same argument. When I differentiate that, the only thing that happens is it comes back to us, and it also produces a times 2 from the differentiation of 2x plus 2. So 6 divided by 2 takes a 3 at the front plus c. Okay, you can use, I guess, the substitution u is equal to all of this, but it'll be very, very silly if you can't see this particular one. Okay, number 77. I don't like the look of number 77 because it's got more trig. 1 minus the cot squared of x multiplied by the sec, is it sec squared? Sec squared of x. Okay. Is this an identity? It looks like an identity, but it isn't. It should be plus. 1 plus cot squared is cosec squared. And I don't know if that would have helped me anyway. But if you look at the bracket carefully, if you times it out, you definitely want to have a sec squared x, and sec squared x on its own is good because we have differentiated it so far several times. So my plan is to multiply it out. So sec squared of x minus cot squared of x sec squared of x dx. I can integrate that anytime I want. The question is this, do I recognize it? Is this something that this combination of trig functions, do they ring a bell? The answer is they don't ring a bell. These two, you don't often see them together. So what I'm going to do is quite obvious. Let me switch them into sines and cosines in the hope that they might simplify to something I might recognize. So a cot will be a cos squared x over a sine squared x, and a sec squared of x 1 over. And it looks like we've got some simplification here. Cos squared, gone. Equal sec squared x, which is nice. We got a minus 1 over sine squared x. So we write it as a cosec, or so, let's actually see it first of all. It's definitely simpler than what we had up there. Sine squared, do we go for a half minus a half cos 2x like we went in the cos squared? The answer is no. Why not? Because this is on the denominator. This particular one, of course, we need to rewrite it. And we need to rewrite it as a cosec squared. And I think I rubbed it off because I had it up there, I think, earlier on. So this, in fact, the 1 over sine squared is cosec squared x. And I'm just going to write it here again. The differential over cot of x is minus cosec squared of x. So when you differentiate a cot, you get minus cosec squared. And here we do have a minus cosec squared. I didn't actually write the sign. I was referring to just the fraction there. So I should really put the sign because it's very easy to miss in there. And therefore my answer will be, to get a sec squared, I differentiate the tan. And to get a minus cosec squared, I just simply differentiated a cot. A cot of x plus c. And let's check our answers as well, because I haven't been checking. I hope I haven't made any mistakes. No, it is correct. All right, let's clear the board. Number 78 is very, very interesting. Loads of trig bits I see up there. I'm getting a little bit scared because often, you know, as the integral will get harder, unless I've prepared myself, maybe I cannot see it and I'm in the middle of a lecture and I'm going to embarrass myself and you'll be laughing at me. So I don't know what this is. It looks very scary. So let's have a look at it. Okay. We got a fraction. The sine of x minus the cos of x over the sine of x plus the cos of x. It looks very scary. Okay, how do we do something like this? I cannot split the fraction in there, all right, because I've got a this 2 bits, so I cannot really split. I can split, I guess, sine x over all of this minus cos over all of this. What other bits I could possibly do? I've got trig, I can go trigonometric identities. Can you think of any trigonometric identities for something like this? The answer is no. I can think of bizarre things such as multiplying top and bottom by sine x minus cos x, difference of squares. You create a cos of 2x at the bottom. I think negative cos 2x at the bottom, and I think it actually might work, actually, believe it or not. I'll actually check it. You're gonna get a very weird answer if you do it that way. But it's not something that you're likely to think or even try, perhaps. We have to look for something a little bit simpler. It can't be that bad. So what other things are there? Okay, this is the very special result, which very often we miss it, is when we have a fractional integrand. Just always check, does by any good fortune the denominator differentiate into the numerator? So remember, I've done a whole lecture on this. If you have this particular scenario, bottom differentiates to top, the answer is always the log of your denominator. Okay, so let's have a little look at this. Sine differentiates to cos. Unlucky, because we got a minus cos. And cos differentiates to minus sine. Unlucky. Double unlucky is lucky, because we have the exact negative of what we need. We can easily manipulate it, and we can manipulate it, of course, as follows. Pull a minus on the outside, so we have a sine x plus cos x, so I'm going to pull it from the top. So if I do that, the cos will go plus cos x, that's my minus cos x as I have it in there, and the sine, of course, is going to go minus sine x, so it's still worth plus. And now, if we check this particular integral, sine differentiates to a cos, cos differentiates to a minus sine, so the answer is the log of this. But don't forget, we've got a minus at the front, so we got minus log mod sine x plus cos x plus c. If you don't see this particular one, because it takes a little bit of training and time to look for some more complicated versions of this type of integral. That was number 78. I forgot to put the number again at the front, sorry. 78. What would have worked here is the substitution. U is sine x plus cos x. It will actually work fairly good. Okay, in 3 or 4 lines, it would have actually given this particular answer. So substitution, always your best friend. Number 79, we're almost coming to the end now. 79, 80, 81. They're actually not too bad, all 3 of them. They're quite standard. 79 is a little bit of a challenge, perhaps. The first time you see it, looks very scary. Sec x, tan x. And then we have the square root of 1 plus, is it plus or minus plus, the sec dx. Okay. What's going through our heads? Well, first of all, the square root is a pain, isn't it? And I don't know many trigonometric identities that have a square root. I don't feel comfortable with this square root. Okay, so I'll rule out manipulating this by trigonometric identities, which of course is telling me perhaps use a substitution, get rid of this square root, because it might simplify things. So in fact, this is the method I will do it. This is recognizable for those who are exam standard, very good in maths or integration, shall I say, not in maths necessarily. You should be able to see this one and just integrate in one line. I mean, that let me just do it first of all by recognition, and then I'll do it by substitution. What you need to see in there, and I'll do one extra line, is let's write the sectan. Sectan is a very important one. It's because when I differentiate a sec differentiates to sec x tan x. I call it sectan. I miss the arguments, I'm very naughty. Okay, so this is my sec x tan x, very important. That's the differential of a sec. And I've got something that has secs in there. I'm gonna write this square root as 1 plus sec of x to the power of a half dx. This is a reverse chain rule. You see the interior of this bracket, when you differentiate it, it produces exactly sec x tan x. So that is telling me I started with a higher bracket of 1 plus sec x. So this starts as 1 plus sec of x to the power of 3 over 2. What happens when I differentiate it? A 3 over 2 will come to the front. The 1 plus sec x will go to the power of a half. Good. And all of this will produce the sec tan. All I need to take care of is that 3 over 2. And therefore, 1 divided by 3 over 2 is 2/3 of this plus c. And the integration is finished. That's all there is to it. However, we might not spot this. So if we go back to our original thinking and say, okay, what would have done for something like this? I would have got rid of that square root. Okay, you can use u is equal to 1 plus the sec of x, or you can use u is the entire square root. Both of them work fine. Let me just do it with the interior, because most people will feel more comfortable with this. So u is equal to 1 plus the sec of x. du by dx. Now you differentiate that, so it's not a case of spotting, it's a case of just looking up in the formula booklet if you don't know what it is. 1 differentiates to nothing, and we got, of course, the result which we got up there. Sec x tan x. Make your dx your subject, so we got dx is equal to du over sec x tan x. And if we need more stuff, we'll come and get it. So let's transform our integral. The sec x tan x at the front, let's leave him where he is. And we called this part u, so that's going to be the square root of u if you want. We could have written it, in fact, we should have really written it as u to the half. I can't be bothered to write it, to rub it off now. And the dx that is following is in fact du over sec x tan x. Is that good? Amazing. Goodbye. And all I need to do, I'm just too lazy. That's my u to the half. And then if I integrate that, it'll be increasing the power by 1. So it's year 12 integration now. And then divide by the new power, it'll give you 2/3 in front of it plus a constant. And of course, you just need to replace back your substitution. And your substitution, of course, was 1 plus the sec of x to the power of 3 over 2 plus c, which of course it gave us again the same answer that we got by recognition, or if you want, reverse chain rule. Okay, number 80. 80 is very, very simple. Maybe I can just fit it here. 80 is the integral of the tan of 2x. Often is being missed. As I said, I use this particular revision book with my own students. I've been using this probably for the last 10 years or so. So I have some familiarity, particularly with the first 100 to 150 integrals, because it's part of the staple diet. Once the integration has finished, all the techniques, that is. So this goes wrong many times. They say, I cannot see how to do this one. This is very easy. The reason you can't do this one is because you're looking for complicated things and you don't know your derivatives. So this is the fact you need to know. When you differentiate a sec, I rubbed it off, it was already there, my god. Okay, the derivative of sec x is sec x tan x. So if we look at this, apart from the argument being in 2x, it's exactly what I've got up there. So this is, in fact, I need to start with a sec of 2x. So I need to differentiate a sec of 2x to get something which looks like that. But of course, this one will produce also a factor of 2. So I need to cancel it. Plus c, 80 is done. And we're going to finish with number 81. 81 is easy, standard, doesn't normally cause problems, and but it does need a bit of space. And we haven't done this type of question tonight. That's the first one that we're doing of this particular type in tonight's lecture. So it'll be good to practice it and remind ourselves how to do things like that. This is the integral of, that's number 81, and the last one for tonight, x squared times the log of x dx. Okay, 81. What's going on with this? Quite obvious what's going on in this. We got a product, and it's two different families: algebraic, multiplying, logarithmic. So there's only one sensible thing to do there, which is integration by parts. And what you must remember, I'll do it with a little grid. You can use your formula, your UVs, the U's, the D's, whatever you call them. I put the item which to be differentiated on the top left and the item to be integrated on the bottom right. But you must remember, if you have a log, as a rule of thumb, you differentiate the log. Okay, so I'm going to put the log of x on the top left, and I'm going to differentiate integrate rather the x squared. Log of x differentiates to 1 over x. X squared comes from differentiation of a third x cubed, or if you want, it integrates to that. So when you set it up in this particular manner, the answer is always the product of these two terms. So that is a third x cubed times the log of x, minus, always minus an integral, and the integral requires to have the product of this diagonal. So if we look at what is a third x cubed times 1 over x, the 1 over x, of course, will cancel your x cubed down to x squared. So that is in fact the third at the front and the x squared inside the integral. And this is a very silly integration. It's a third x cubed log mod x, and this comes from an x cubed. We need another divide by 3, so it's going to be a minus 1/9 x cubed plus c. And that's question number 81. By the way, for those who really are flying and they really want a challenge, the challenge that I'm going to put, it can be done. Can you, actually I'm not going to put a grid in there. I will put a grid. Can you do this question by differentiating the x squared and integrating the log of x? And you may use the result that log of x integrates to x log x minus x. So you don't have to prove it, but that differentiates to that. And of course that will be quite clearly 2x. Can you do this integration by parts for this particular one using this setup? The answer is yes, it can be done, but it's just a little bit of a kind of like fun rather than sensible to do in a question. I mean, this, as you can see, is 3 lines. This will take several lines, but it's definitely doable. Okay. Keep revising. This was, I think, lecture number 7. I probably got for maybe up to about 10 lectures. I don't know how many of these integrals I will fit in. I hope you find them useful. And on this note, who's laughing now? I'm definitely laughing. I've finished for the day. It's Friday night. I'm having an early night tonight, guys. Join me soon. Okay, bye for now.